All right, let's get started for today. A couple of announcements for CS188. Final prep page is up. Check it out. There is a lot of extra office hours next week. Check them out. If anything is still unclear, come and ask us about it. There are past exams. There is a practice final, which similarly to what we had for midterms is you take the practice final, submit it online. If you satisfy the requirements, you get 1 extra credit point on the actual final. That's due 5/10. There's also Project 5. As you know, probably by now we have a drop the lowest policy. So you get to drop your lowest project score, get to drop your lowest homework score. So if you want to be done with projects and homework, you can be done, but we encourage you to try them out. They're exciting and interesting. There's Project 5, which is on machine learning, and there is also actually, homework 10 is just done, that was yesterday, and then there's a final contest, which was finished on Sunday in terms of your submissions, and we'll see the results on Thursday in lecture. Any questions about logistics? All right, then let's take a look again at some AI in the news. Almost like clockwork, as we covered autonomous driving last week Thursday, Google came out with an announcement yesterday, a new post on their blog about their autonomous cars. They announced essentially that they've made a lot of progress for city street driving, meaning that they've been running a lot of experiments in Mountain View, which where the headquarters are, so easiest for them to experiment, also not the most difficult city, I guess, to drive in for now. And they made a lot of progress, and they released a video illustrating some of the things they can do now. So just want to share that video. This is this was released yesterday by the Google self-driving car team.
I'm Priscilla, one of the test drivers on the Google self-driving car project. Our team is responsible for keeping the cars and other people safe while on the road, and for providing feedback on how they perform in the real world. A big part of our job is to go out into the world and uncover all the potential scenarios that a car might encounter. Then we help the engineers teach the car how to best navigate each one. Here are some examples of situations that we regularly encounter on the streets of Mountain View, California. We've taught the vehicle to recognize and navigate through construction zones. Our sensors spot the orange signs and cones early to alert the car of the lane blockage ahead, and we can change lanes safely. You'll also notice the vehicle typically moves to keep a safe distance away from large obstacles, like this truck stopped on the side of the road. Now we're approaching a railroad crossing, which requires special care. Notice the red fence and railroad sign that appears to the computer as we approach the intersection. This means that we'll wait until the tracks are clear of other vehicles before proceeding. Our cars treat cyclists as a special category of moving object. Watch in this example, when the cyclist holds up his arm, our software detects the hand signal and predicts his movement into our lane. The car knows to continue yielding to the cyclist passing by, even when he changes his mind, multiple times. So now what you'll see is our vehicle at a busy intersection. Here the cars are represented by pink boxes, and the cyclists and pedestrians are the red and yellow boxes. Now notice the boxes moving past us. It's the cyclist and pedestrian's turn to go. The red and green fences indicate that the car will stop and wait until the path is clear. We even detect the cyclist approaching from behind and wait until they've passed. Once the cyclist has gone by, the vehicle determines that it's safe to turn. We still have more work to do, but it's fun to see how many situations we can now handle smoothly and naturally. See you on the road.
So one thing I want to announce, if you're particularly excited about robotics, is that there are 3 top-tier robotics conferences, academic conferences, ICRA, IROS, and RSS. RSS this year will be in Berkeley. So if you wanted to attend the top-tier academic robotic conference, it'll be in Berkeley July 12 to 16. RSS stands for Robotics, Science, and Systems. The student registration fee is only $250. It's a 5-day conference. It includes a cruise on the bay on the Tuesday evening of the conference, and it includes Google X picking up conference participants on Wednesday evening, bringing them to the Google X headquarters and giving a bunch of presentations there about their projects, and also having a raffle to take a ride in one of their self-driving cars. Not sure how many people will win the raffle, but definitely at least there will be some winners. So if you're interested in robotics and want to see something in terms of the latest research, this is a good opportunity because these conferences move around every year, and RSS just happens to be in Berkeley this summer, July 12th to 16th. Okay, we looked a little bit at robotics last time. We looked at self-driving cars. Today we're going to look at more robotics, and we're also going to look at computer vision, and we'll start with that. So, computer vision. It's about making a computer see, and in particular understand what's in images. This is actually a pretty difficult problem. The problem of object detection, the problem of a computer finding in an image what's there is very difficult, because for a computer, all it sees is just a bunch of numbers. It's just pixels or numbers, and a computer a priori doesn't have any concept of any object we might want to detect. So we'll take a look at two state-of-the-art type approaches to detect certain types of objects in images. The first approach, HOG plus SVM, which is representative of a whole class of approaches, proceeds as follows. SVM we've seen before, support vector machine. It's a generalization of Perceptron where you consider all data at once and find a decision boundary that separates the data all at once. Now, HOG is kind of something computer vision specific, and in general, when you do machine learning, you'll see that in practice, things like SVM, Perceptron, naive Bayes, and so forth, those are just implemented in a toolbox for you. You just use that toolbox, and it'll work just fine for what it's asked to do, which is learn a decision boundary given some training data. But the really hard part will be to somehow take your training data, featureize it in a good way such that now your learning algorithm actually can learn something meaningful. So for example, for images, if you just feed raw images into a support vector machine and you hope for the support vector machine to learn, let's say, where a person is in the image or maybe where a baseball pitcher is in the image, it's not going to have a very easy time to somehow make that work. It's going to be very difficult. The reason that is because pixels can vary a lot. Even for the same scene, a different lighting condition will make all pixels different, but still the same thing is in the image. So you somehow want to detect the same thing in the image even though all pixels have taken on different values. And so what you really want to do is somehow come up with a feature-based representation that is capturing the invariants that you are aware of. For your project 5, you can have things like with digits. If you do digit recognition, you might, let's say, rotate a digit, or in here a person, you might shift the person in the image and say that should still be the same person and so forth. So how can your features capture these invariants that you are aware of but a computer a priori has no knowledge about? Here's one way to do it. What people found is that a lot of the information is captured in the edges of the image. So often the first thing that happens is you pass your image to what is essentially an edge filter, and you get out this image shown in the middle there, which just shows the boundaries of the person and some other boundaries of parts of the person. How do you do that? The way you do that is, simple way to do it is to take finite differences. For every pixel, you can take the difference between the pixel to the left of it and the pixel to the right of it. That's a derivative, effectively, that you're computing. And wherever derivatives are high is where you have boundaries between different parts in the image. Where the derivatives are low, you have a smooth part of the image where you don't have a boundary. You can do this left-right. You can do this pixel above, pixel below difference. So you have an X direction, finite differences, Y direction, finite differences. You can square and sum those finite differences, and then you get an image like the one shown over there. In practice, you might not want to just simply square and sum them. You might want to keep around both derivatives, the one with respect to the X direction, the one with respect to the Y direction. So you have a two-dimensional quantity at each pixel, which represents the gradient in the image. If you do that, you keep around that two-dimensional quantity, which represents the gradient in the image. Then the next step you take is this one here. What happens here is you say, well, if let's say I have something in an image, let's say I'm trying to recognize a person. If the person is a little skinnier or a little fatter, it's still a person. So you might want to build in the invariant that the edges could have shifted a little bit. So you don't want to just have an edge image, because now you still haven't encoded the fact that edges could shift and it could still be the same thing. And what this is doing is building histograms. This is looking at regions of the image. So there's a region here corresponding to, let's say, some region somewhere over there. In a particular region, it checks for every pixel what is the gradient at that pixel. Then it builds a histogram of gradients, and you're shown the histogram of gradients in this region, same thing over here, and so forth. How do you compute this histogram? Well, you have to discretize. All right, so you pick, for example, you bin things according to 8 directions, and for each gradient that you found in a particular part of the image, you check which of the 8 directions is the closest to the direction I found, and you assign it to that direction. Or you might do soft binning, where you say which are the 2 closest ones that surround it, and then partially assign it to each of those bins. You might say, well, the discretization, do we lose some accuracy? And the truth is, you lose something about the original image. But what people have found is that it's a good thing to lose. Because if you're off by a couple of degrees in terms of how the edge is angled, that actually doesn't change what you're looking at in the image. So you have a feature representation that's more robust in this way by having it binned rather than the original edge directions. So we did 2 steps here. The first step was going from the original image to essentially an edge image. That's extracting what we think of as the essence of what's in the image, and we can still see what's there. But then the next step is to help the machine learning algorithm even more, to help it generalize even better. We now start binning things by building histograms. Okay, let's take a look at if we can still recognize things. So here's a hog image of something. Any suggestions of what might be in this image? I hear bicycle. Who thinks bicycle? Okay, so this is great. Even though we are not computers, and maybe computers think differently, at least we have a sanity check here that we all think, or most of us think, there's a bicycle there. And I should take a peek at what the original image was. Indeed, there was a bicycle there. So we somehow got rid of a lot of the information that was there originally, reduced it to something that's more robust. It captures the essence of the shape of a bicycle, and we can still recognize it. And that hopefully means that the machine learning algorithm will still be able to recognize it, have enough information there, and also be able to avoid overfitting to specific pixel values or specific locations of the edges. All right, so how does this work? You've seen the whole concept, right? You have data, you split it into train data and validation data, and then test data is what you kind of have later to see what you really are able to perform. So what do you do with your training data? We've done so far is we've said, well, you take your training data, you have some labeled, let's say, bicycles, and then some labeled non-bicycles, and you would just learn a classifier for a vector machine or Perceptron, naive Bayes, whatever you prefer. In practice for images, even when we go to this hog-based representation, it's still a very high-dimensional feature space. So you need a lot of data. So often part of the game of machine learning is to find a way to come up with a lot of meaningful data. So one trick you might play, for example, for images is you might go out and do a Google image search for bicycle. That might give you a lot of images in the top ranked returns that have a bicycle in them. Might be some that aren't bicycles. That could be noise, or you could take them out, whatever you want to do. That would give you your positive class. You have labels, images labeled with bicycles. Now we also need a negative class. You need the examples that are not bicycles. For that, you can actually take almost infinite amount of data. Right? Almost every picture will not have a bicycle, so you just mine lots and lots of images and use those as negatives. Then you train your support vector machine. So you compute hog representation on all your images, train your support vector machine to classify between bicycle and not bicycle. There might be some tuning parameters, which you use your holdout data to set your tuning parameters. Then the next thing you do is to get better performance out, you start focusing on your mistakes. So you learned your classifier, you now apply it to a wide range of extra data, and you check if ever it detects a bicycle where there is no bicycle. If that happens, you grab that data where that happens. Those are hard negatives. Those are the things you're getting wrong. Things that with your original classifier look like a bicycle, but actually aren't. And you feed that data on top of your original training data in a retraining of your support vector machine. And you can potentially repeat this multiple times. But the key idea here is that you mine for the examples that make it really difficult to get right, that are difficult to get right. And that way, when you retrain with those examples, you zone in on your decision boundary, and you can get a more accurate classifier. Right, so what kind of results can we get with this? Here is some typical examples. So the top row is a classifier that was trained to detect sofas in the way I just described. And then it's applied to images. So the first one, so I should say one extra thing here. Rather than just training a classifier to detect sofas, there's a little more detail underneath there, and you see this in these boxes here. So the sofa consists of 6 boxes sitting inside a bigger box. What that means is that effectively what they trained here was 6 classifiers. Thinking of a sofa as consisting of 6 parts, and each part could be shifted a little bit relative to each other. So it's detecting the top right of a sofa, the middle top of a sofa, the top left, and so forth. And then if it finds all 6 parts, then it checks if they are in the right locations relative to each other to really detect a sofa. So there's a little more going on than what I told you, but effectively, they're using support vector machine training and this hog representation as well as training specifically to have parts to detect sofas at the top here. So first one is good, second one is good, third one, not so good. These are cats sitting on what seems to be a windowsill. Looks like a sofa to this classifier. This, you might argue, is not a sofa the way it's defined as something bigger. Let's look at bottles. First one here, pretty good, finds the ketchup. Next one finds some bottles too, that not bad. Same here, detects them, but then here it finds a bottle right in the middle of a license plate. And then over here it thinks this cone is a bottle. So this looks funny to us because for us it's really easy to recognize things in an image, but from an AI point of view, actually this is doing pretty well. This is a very hard problem to recognize things reliably in an image, and this is state-of-the-art performance as of, this is for about 2 years ago. We'll later get to some of the things that are state-of-the-art right now. But it's still comparable to what people are able to do now in terms of performance. Here, last one is detecting cats. For that, of course, there's a lot of training data, a lot of positive examples, so that can work pretty well. People, so see some examples of people detection here. It works reasonably reliably, but it fails to find some people that are kind of occluded by their musical instruments. Naturally, if you hold something in front of yourself, it's going to be more difficult to detect that you're still there for the classifier, because there will be additional edges, and it'll somehow have to learn that those additional edges don't preclude you from being a person in the image. Cars, so let's take a look here. First one is good. Second one, all right. Third one is okay. The fourth one is not a good one. So here it found a lot of parts of car, but they're not really organized as one car. It thinks there is one car there. That's what the detection is saying, but really there is 2 cars there, and it kind of conglomerated them together as one detection. And then here, again, it finds a bus, which qualifies as a car. Last one, horses. So the first 3 are pretty good. This one here is technically a cow. And this here is a part of an airplane that happens to look like a horse. All right, so in some sense this is exciting. If you like AI, you like to improve the state of the art in artificial intelligence, here's a domain that still can benefit from a lot of improvement, and it's something you could think about working on. Okay, there's a second line of work that's seen a lot of good results lately in computer vision, and this is called deep learning. And the idea there, the high-level idea is that, well, something like HOG is really cool, and people in computer vision essentially kind of worked for 10, 20 years to build up to something like HOG that captures invariants about what you see in an image so a classifier can work better. It's really tricky and requires a lot of expertise to still not do all that well compared to human performance. And so a lot of people start looking at, well, if it's that hard, even for very experienced computer vision people to come up with the right features, can we come up with a way to learn the features themselves? Because if we can learn the features, well, then that's great. The computer figures them out on its own, and we don't need to specify them by hand. And the reason people started thinking this might be possible is that we have a lot of data. If you look at computer vision before the internet age, right, you had a couple of images to work with. It was very difficult to apply machine learning at a large scale because you didn't have the data. But right now, billions of images kind of surface pretty much every day on the internet. And if you can just download those and somehow use all of them, there might be enough signal there that you can learn the features too, and you don't have to hard code them. Okay, so the story here, New York Times story from 2012, says, how many computers to identify a cat? And the answer was 16,000. All right, so technically it was 16,000 cores at Google that were used to identify cats in images. Okay, that's just the headline. What was really going on here? What was going on is that they were working on this idea of learning features, using something called deep learning, which is the standard way to learn features these days. And they essentially deployed a system that used 16,000 cores at Google, a lot of data. They downloaded a lot of images from YouTube videos, applied deep learning to that, which is something I'll explain in more detail soon enough. And then what came out of it was a big neural network. So a bit like a brain in some sense. They like to call it the Google Brain Project. Not an actual brain, of course. It's just a neural network. And that neural network had neurons that fire for the presence of a cat. So if a cat was in an image, a certain neuron would fire, meaning that somehow the neural network learned what it means to look like a cat. All right, so what it looks like is a lot like a perceptron, but then many perceptrons networked together. So let's review what a perceptron was. A perceptron was something where you have a bunch of inputs, then each inputs get multiplied with a weight, then the weight times feature inputs get summed together, and you get an output. If it was bigger than 0, it was positive class, less than 0, negative class. Okay, you can sequence these together in a more complicated way. Think back to the computer vision type of things we looked at just now. Let's say you want to recognize something that consists of 3 parts. You can imagine that a structure like this could do the job. You have first 3 perceptrons in parallel that fire on each of the 3 parts individually. And then if all 3 of them fire the right way, then the last one fires to say, yeah, all 3 parts are present. I recognize, let's say, a sofa or a cat and so forth. 3 parts is maybe not the right choice, of course, but this is just a picture that fits on the slides. One thing I want to say that's different from the perceptron and that's being used in these representations here is that it's not a 0, 1 kind of thing or a negative, positive kind of thing. If you look at these units here, it's a gradual transition. So it smoothly transitions. For very negative values, it's 0. For very positive values, it's 1. So it transitions from 0 to 1 in a smooth way. You can make it negative 1 to positive 1, but the important thing is that it's in a smooth way, not just a perceptron that jumps from negative 1 to positive 1. Making it smooth will be important later. But that's just a minor difference. In terms of representation, it's just important for the learning, the training procedure. Okay, so a neural network could look like this. You could have many of these layers where the way we interpret this for an image would be you have pixels coming in, not just 3 pixels, but let's say a 256 by 256 image would have over 4,000 pixels. Those are your inputs. Then there is a first layer sitting over here. That first layer has a bunch of perceptrons that are now soft perceptrons, because it smoothly transitions from negative 1 to positive 1. Then from there, their outputs get fed into a next layer of smooth out perceptrons, and this keeps repeating for many, many layers until at the end you make your decision. Intuitively, what you want to be happening in this representation is that somehow the first layer maybe captures something local. The first layer could capture whether a vertical image is present. So this could capture maybe, is locally in this region in the image, this 16 by 16 region that I'm connected to, is there a vertical edge? Then the next one could say, well, in my 16 by 16 region, is there a vertical edge? And then the next one might say, well, in my 16 by 16 region, is there a horizontal edge, and so forth. It's not hard-coded that way, but the idea is that these things could be represented by this kind of architecture. Then the next layer might be something where it says, well, did I see a vertical edge and a horizontal edge in my 16 by 16 patch? The next layer could then be, did I see another combination of corners, and so forth. And by the time you get over here, you might get units that look at something like, am I seeing a face here? Am I seeing a cat face here? Am I seeing a wheel of a car, and so forth? And then the last unit can see whether the right things are present to make a decision about a car being present or a cat, and so forth. So that's the intuition. Making this happen by hand is effectively what's happening with Hog. With Hog, what would happen is you'd essentially hard code the equivalent of the first two layers, and then go straight from there into your support vector machine. What's happening here is we have the first two layers. We're not going to hard code them. They could represent something like Hog, but actually won't exactly represent that. But then we keep going. We say, well, if it can learn how the first layer works, which was shown in early experiments, then it can probably learn how the next layers work too. And that way we can get a much more detailed representation at the beginning and coarser at the end that somehow allows us to recognize things more robustly. Of course, just like we saw in Perceptron, each of these units here has weights on them. So there's a weight sitting right here, and there's a weight on every one of those edges. Often there's up to 1 billion, maybe more weights sitting there that you somehow need to train. So you can imagine you need a lot of training data for this to work. If you're going to learn 1 billion parameters, probably need lots and lots of images to be able to set those parameters right. Okay, so how do you train this? The way you train is use something called hill climbing. We've seen that before. What does that mean? You have a current set of weights. For the current set of weights, you go through your data and see how well you perform. You have some accuracy in terms of predicting what's in the image. Then you perturb your weights. You see how well you now perform on your data. If you do better, you keep it. If you do worse, you discard that change. You keep repeating. That's a naive way of hill climbing. That would take a little longer than you'd want to for this kind of millions or billions of images that you want to feed through this, but that's the main idea. Now for this to work, it is important that your landscape that you're optimizing over doesn't have too many plateaus. Remember, plateaus are these regions where if you move a little left, a little right, it still looks the same, the score is the same. That's why we need to switch from the old Perceptron that we had that triggers to -1 or +1, depending on lower or higher than 0, to something that's smoother. If you have something smoother now, if you move the weights around a little bit, your score will change at the end, rather than stay the same for a large stretch. So the smoothing out is important for the hill climb. The actual hill climbing, the way it works, would be happening a little differently in that since people look at so much data, they often look at mini batches at a time. So rather than evaluating a current set of parameters on all your data and then perturbing them and again looking at all your data, you would look at a small mini batch. On that mini batch, look at your current parameters performance, look at your changed parameters performance, see which one's better, keep that, move on to the next small set of data and the next perturbation. It's a stochastic approach because now you're not looking at all your training data at once. But this still tends to work and finds a good optimum in many situations. Another thing people do differently, rather than just randomly perturbing the weights, people will take analytical derivatives. So rather than just perturbing the weights and seeing whether it's better or not, you take the derivative of your scoring function with respect to each of your parameters, and then move your parameters in a direction that increases the score. Okay, even with all that in place, sometimes there are extra things you can do to make this work better. And one thing that's been quite popular is this auto-encoder idea. what's the idea here? The idea here is that, let's say you have a certain amount of images that are labeled, and there's a car in the image, versus a boat, versus a cat, versus a person, and so forth. At the end of the day, that's not a whole lot of information. You had this whole image, entire image, and now you're saying that was a boat. If you had, let's say, 1,000 categories, then it'd be essentially log 2 of 1,000 in terms of information. So very little information that you retain in terms of information bits from your image. All you're doing in naive training, so to say, is go from this rich image to this label that has very little information left. Although ultimately that's what you want, people start looking at other ways to leverage the information in the image. And they would say, well, how about instead of training a neural net to predict the label, train a neural net to predict the image itself. If you have a 256 by 256 image, now you're predicting about a 4,000 pixel values. That's a lot more supervision, a lot more training data that you have available to yourself than just the label. This is called auto-encoders if you build it this particular way. So what happens here is you still have, here I show 4 images being fed into the auto-encoder. The auto-encoder is a neural net that takes in an image, computes features from it, and then decodes from the features back to the image. And its objective is to match what's here with what is over here. You could say that's very easy to do. You just pass through straight what you get, and you'll have a perfect match. And that's indeed a way to have the perfect objective in terms of reconstruction. So people add an extra term to the objective. The extra term is one that says that the units that you look at over here, which are the feature values that you compute, have to be activated in a sparse way. So only a few of them can be active for any given image. So it's requiring you to somehow compress the information in your image to fire only a few features and then asking you to do so in a way that from those few features you can reconstruct the original image as accurately as possible. So you can train this, you can find features. If you do this, you actually find features very similar to, essentially, you find edge detectors if you run this. It's a nice confirmation of the fact that people spending a lot of time in computer vision, they found that edge detectors are very robust and a good thing to represent your image, at least at the fine-grained level. Same thing is being found here. But actually, now you can take the next step. You can repeat this procedure. And so rather than just learning a first layer of features, you can do this in a stacked way. After you learn your features using an autoencoder, you can now transform all your images in your feature representation of your images. You take those feature representations of your images and you can apply the same procedure. You're supposed to somehow auto-encode them and decode back to that feature representation. And now you get a higher level feature that's at the next layer in the abstraction. You can repeat this multiple times. You have multiple layers of abstraction, higher and higher level features. That's a common way if you have a lot of data that doesn't have, especially if it doesn't have labels, that you can leverage all that data to somehow train a stacked autoencoder, which allows you to encode your image into low-level features, mid-level features, high-level features, and then back out the original image. Then what you do is, instead of backing back out the original image, you stop at the high-level features, you put a support vector machine behind it, and you train your support vector machine. If you do what I just said in terms of kind of the stacked coding, and there's something else that I should mention that it's actually important too, is this pooling. So what we talked about so far is that you kind of use something like a Perceptron to find features. Usually after you do that, you do some pooling. What that means is, let's say in a small region of the image, you have a bunch of features, right? Let's say they're all trying to find a vertical edge, right? Then you want to pool that together, just like in Hog, where you didn't want to be specific to the exact location of the edge. Same thing here, you want your representation to be such that it pools the outputs of multiple perceptrons and takes the maximum of that set of pooled units. So you might take 16 perceptrons and pool their outcome and have a new outcome that's the maximum of those 16 outcomes. And if you do that, that's an extra layer that you insert between all the layers we had so far. Those 16 will end up being trained. When you train them, they'll end up representing things like all our firing for a vertical edge, or all are firing for a horizontal edge, and then the pooling makes it invariant to exactly where that edge appears. And this also happens with the higher level features, same for faces, arms, and so forth. You have that pooling that makes it invariant to exactly where these parts appear. All right, so if you do this, and then inspect what's in this neural net, that's always interesting to do, right? What did you learn? Well, here's one thing you can do. You can take an image, let's say an image of a cat, right? Or actually, let's take one step back. You can take all your images, feed them through your neural net, and see which unit at the very last layer fires most frequently. That probably captures something that frequently occurs in your images. All of them will fire sparsely because we enforce that. None of them can fire all that often, but among all of them, one of them will fire the most often. You can look at that one, right, and you can see, well, the images that make this unit fire the most, what are those images? Because those images are in some sense unified by this network into that unit firing. Right? You can do this, and if you do that for all these YouTube videos, images, what they did at Google, what you get is that faces will correspond to what you see as the most frequently recurring thing that one of these units at the end is representative of. Then look at the second most frequent thing, you'll find this, cat faces. So that's what they found, and I guess they found the cat face thing probably a better hook to get visibility in the New York Times than people faces, so that's what they went with in that headline. And what they think is if they used more data, then, so for now, in some sense, there was only enough data to reliably find people faces and cat faces. If you had more data, more diverse data maybe, then you'd find more and more features related to other things that you might want to find in images. Now, of course, it's very easy to train a cat detector. We haven't learned a classifier yet, but once you pre-train this, that's what it's called, pre-training, you can now hook up a sport vector machine or a perceptron at the end, and with those kind of features, if one of your features already knows that it's a cat face, very easy to now train a classifier for cat faces. All right, let's take a break here, and after the, actually, no, let's take the one question. There was a question over there. Patrick, do you still have your question? Okay, it's a good question. So to which extent are images being reconstructed in this training procedure here? Effectively, what happens is that there's a scoring function. That scoring function measures the difference between the original image and the image that's the reconstruction of the original image. And the optimization procedure will find a set of weights that performs as well as possible on the reconstruction metric, but it will not be perfect. There will definitely be differences. And at the same time, ensures that the features that are being learned only can fire sparsely. And so there's a trade-off there, and there's a tweaking parameter there that you tweak in terms of how much do you require sparsity versus how much do you require reconstruction of the original images. And the right thing will be somewhere in the middle where each of them gets enforced to some extent, but you're not fully reconstructing, you're not fully making everything completely sparse either. All right, let's take a break here, and after the break, let's look at robotics. All right, let's restart. Any questions about the first half of lecture? All right, let's take a look at robotics then. What we're going to look at today in robotics is robotic helicopters and walking robots. Both of which I actually worked on quite a bit myself in my, for my PhD thesis work. And we'll see a lot of that work here, and I think a lot of it is still the state of the art, even 5 years, 6 years later. So, let's see here. Robotic helicopters. So this is what we want to go after, is somehow fly helicopters in their entire flight envelope, including upside down and whatever else we might want to do. So the question then becomes one of, to make this happen. That was kind of the task we were after during my research there. Just kind of, nobody had done this with an autonomous helicopter, so the question was how to get helicopters to do these kind of things. So where do you start? Well, place to start is, of course, to get a helicopter. I've since repainted that helicopter in blue and gold. So what are the key challenges when you fly one of those helicopters? Well, one thing is you need to keep track of the helicopter. You need to know its position and orientation over time. Otherwise, it's very difficult to control it. Another thing is, even when you know position and orientation of the helicopter, you still need to decide on what the right actions are. That's a lot related to search and reinforcement learning and so forth, what the right thing is to do there. How do you control the helicopter? So what we have there is a standard remote control with 2 sticks. So sometimes 4 control inputs because each stick has 2 degrees of freedom. In the US, the way it's set up is that 1 stick is your collective control and your tail rotor control, the rudder. What that does is it changes the angle of attack of your main rotor. So your main rotor can have a varying angle. If you make it, let's say, very positive, you push a lot of air down. Make it very negative, you push a lot of air up. That's how you control the thrust of your helicopter. You do the same thing with the tail rotor. The angle of the blades determines how much air is being pushed sideways, and so you can control that angle, and that way you control the amount of air pushed sideways, and you can spin your helicopter tail around, or really what you by default are doing by pushing air sideways is to keep the helicopter from spinning in the counter direction of the way the blades are spinning. Because if you apply torque to your blades, they're going in one direction, normally your helicopter body will go in the opposite direction, so the tail rotor is preventing that from happening. Then the other thing you want to do with a helicopter is you want to move around, right? You don't just want to go up and down and look in different directions, you want to go somewhere. The way that's done is by using the cyclic controls. The cyclic controls are on the other joystick, and what they do is they change the angle of attack of the blades, the main rotor, cyclically throughout the cycle of the main rotor going around. So for example, you could have a higher angle of attack on one side and lower on the other side, or maybe higher in the front, lower in the back, and so forth. This way you get differential thrust, front, back, left, right. What that allows you to do is to rotate your helicopter. You can rotate it, roll it, or pitch it. Once your helicopter is, let's say, pitched forward in that direction, now the vertical thrust in the helicopter frame will not just compensate for gravity, but also make it go horizontally forward. That's the way you go forward. You have to have your nose down, otherwise you can't go forward. Okay, so effectively what you control is the angular rate of your helicopter around the 3 main axes and the vertical thrust. And then velocity in the non-vertical direction you get by somehow reorienting your helicopter. Okay, so that's the problem we're faced with. It is true that you can also control the engine of the helicopter. You have a setting there. You can say, what's the RPM of my helicopter blades? Maybe 1800 RPM, so 30 times per second the blades go around. That would be a good setting for this one maybe. You can control that. But the engine tends to be built for a certain RPM. And so it's good, you don't control your RPM to control your helicopter. It's kind of just, oh, I want an efficient engine at 1800 RPM, it's efficient, that's what I'm going to use, and you don't spin up and down the engine to accelerate your helicopter. Your engine is controlled on your helicopter locally. If you ask for a steeper angle of attack, sure, your engine will have to do more work to keep pushing the blades around, because now pushing more air down. There's a local controller on the helicopter that then somehow makes the engine output more power so that it still goes around at 30 hertz while pushing down more air. But as a pilot, you don't directly control that. That's happening on the helicopter. It's just adapting its engine input as a function of how much thrust you are generating by changing the angle. Also keep in mind, spinning up and down an engine would take a really long time. So aside from the efficiency reason, keep your engine at constant RPM, there's also the reason that it's just not very reactive. If you have to spin up and down an engine, it's going to take a long time to accelerate. If you just have to change the angle of the blades, that's very quick to do. All right, so you have your remote control, sends controls to the helicopter. You have a computer on the ground that can decide what to send to the helicopter. The way you get into that remote control is a port in the back. That port is normally used for another pilot. So let's say you're a good pilot, you hold that remote control over there. Then the novice pilot would have their own remote control, go in the back of the good pilot's remote control, and the good pilot can now decide whether their controls are being sent on, then well, the novice pilot's controls are being sent on to the helicopter. So it's a relay system, but the expert pilot can always take back control if they want to. For example, a computer is not doing well, expert pilot can abort computer control, take control themselves and save the helicopter. Then for the computer to know where the helicopter is, we have sensors on board. There's an inertial measurements unit, which measures 3-axis accelerometer, which measures acceleration, but really what it measures is 0 if you're free falling for an accelerometer sensor, and if you're not free falling, it measures whatever it is that's different from free falling in terms of acceleration. If you're standing still, it'll measure 1g because you're not free falling by 1g. Then you measure angular rates, 3 axes, so you measure how fast your sensor is rotating around each of its 3 axes, and you measure magnetic field. Again, a 3-axis sensor, what that is measuring is the angle of your sensor effectively relative to the Earth magnetic field. The Earth magnetic field to some extent points north, but also points into the Earth quite a bit actually. There's some inclination there. So you measure orientation of your sensor relative to the Earth magnetic field. It doesn't give you full orientation, because there'll still be 1 degree of freedom left in your orientation that you don't know, which is rotation around the Earth magnetic axis. But 2 degrees of freedom of orientation you get out of your magnetometer. Now, another thing we measure is position of the helicopter. So we use cameras. You could use GPS. GPS can measure position quite well, especially if you're in upright flight. Once you start flying very aggressively and you're flying upside down and so forth, your GPS antenna will lose its lock on the satellite signal, and you will not have a very accurate localization, which will be problematic. The main reason it's actually really important to have accurate localization for a helicopter is that if you think about what's going on here, you have this accelerometer, right, and magnetometer. Together, effectively, they provide you orientation of the helicopter in a noisy way. But the accelerometer is actually not measuring orientation. The accelerometer is just measuring how much you are accelerating relative to free falling, right? And so when you look at your accelerometer readings, right, some of it is actual acceleration, right, and some of it is just because it's relative to free falling, right? Free falling is 0 acceleration. So you somehow effectively, if you get your position, what you know is your true acceleration. And if you combine it with your accelerometer readings, you can actually back out orientation pretty well. But if you don't have both position over time, which effectively gives you actual acceleration over time, and accelerometer readings combined, just accelerometer readings are not going to give you enough information to get the orientation of your helicopter out. Okay, so we have position readings. We use a Kalman filter, which is a type of a hidden Markov model where the variables are continuous and the distributions are assumed Gaussian. We use a Kalman filter representation in our HMM to track the helicopter. The state variables are position, orientation, velocity, angular rate. The observations are the things I just mentioned on the previous slide. And just running probabilistic inference does the right thing to get out state estimates. Right, so we have a dynamics model, of course. That's the transition model in the HMM. That is modeling helicopter dynamics. Yes? Say that again? Well, a helicopter for any given location could be in any orientation still. So just knowing the location of the helicopter is not enough to know its orientation. So we need, as part of the state of the helicopter, we need its orientation. Those are the phi, theta, psi, are 3 numbers that represent orientation. For any rigid body, for that matter, you need both position and orientation, as well as their time derivatives to get the full state of the rigid body. Helicopter is not a rigid body because there are things that are spinning, but it can be modeled reasonably well as a rigid body if you do it this way. Question? So we don't directly measure velocities. So the way we measure position is height, Z, So the vision system has multiple cameras looking at the helicopter. If you know where they are, you know how they're set up, and you detect the helicopter in the image, you can triangulate to find out where the helicopter is in 3D space. So that's how that's done. GPS can do it too. GPS knows height also, but we're not doing it with GPS in the experiments I'm talking about here, just because to get accurate GPS localization, you need to lock on to the carrier wave of the GPS. If you do that, you can get about maybe 2 centimeter accurate localization. That locking onto the carrier wave cannot be done robustly if you're accelerating, or nobody has a system that does it robustly. In principle, of course, it can, but there isn't such a system that does it to lock on robustly if you are accelerating quickly and if you are changing orientation such that your antenna is not seeing the GPS satellites at all times. Okay, so then we have to solve a market decision process to find a control policy, right? So we know about that. We have the actions, which I described, 4-dimensional action space. Someone want to find a mapping from states to actions that does well. What do we still need? Transition model, that's helicopter dynamics. It's actually pretty difficult to model helicopter dynamics and to get an accurate transition model. I'll tell you a little more later about how we got an accurate transition model, but for now, just assume it's there. And then we need one more thing to solve this MDP, which is a reward function. All right, we need to specify the task. You can do many things with your helicopter. If you want to do it something particular, you need to specify a reward function that encodes that particular task. So let's say we want to hover. What could be a reward function for hover? Well, hover means you want to stay in place and level, right? But the main thing is staying in place. So maybe your reward function is something like this, where you say, well, I'm going to have negative reward whenever my state is away from the target state. So the target state is X star, Y star, Z star, and then we want to be in that location. If we deviate from that, we penalize, negative reward. If we deviate from 0 velocities, we penalize for that. And then a solution to this would be a policy that helps your helicopter stay in place then. All right, so let's take a look at this all in action. So run, in this case, reinforcement learning in simulation. After running it in simulation, when you found something that works well in simulation, put it on the actual helicopter and see what helicopter is hovering upside down. And we know how that works, right? You can use a negative angle for the collective control input. That will push air up in the frame of the helicopter. But if the helicopter is upside down, it'll push air down and keep helicopter in the air. And as I might have mentioned at the end of the reinforcement learning lectures, is that this is actually the more efficient way to fly. The reason it's the more efficient way to fly is because you pull air in and then push it out at a higher pace. If you pull air in this configuration, it's going over the helicopter body, dragging it down, but it's going slow still. Whereas if you're in a regular hover, as you push your air out, it's going very fast, and now it's going over your helicopter body when it's going fast, which will drag your helicopter down. It's probably about 10% more efficient to fly this way than the other way around. Okay, this is all good. We saw a helicopter hover upside down. But of course, the real question here, if you watch this carefully, is, well, who flipped the helicopter? Because this helicopter was, even though it maybe looked straight up, it was just a camera that was rotating. A camera was flipped, no helicopter was flipped here, right? The question is, can we actually build a controller that also flips the helicopter rather than keeping it stabilized? So think of what's going on here. Hovering upside down is a lot like regular hover. Effectively, the way the helicopter works is you have a main rotor and you have a tail rotor, And just the mass ends up being above the main rotor versus below, but the way it works is actually quite similar, whether it's upside down or not. Question there? I don't know how it was originally discovered, but the models for the aerodynamics of a helicopter tell you that airflow, kind of a back of the envelope crude calculation for ideal models, is twice as fast below the main rotor disk compared to above the main rotor disk. So the outgoing velocity is twice the ingoing velocity. The amount of drag a surface incurs as a function of the amount of the airspeed over it is squared in the velocity. There's a factor 4 more drag over the helicopter body when it's below compared to above the helicopter. Now that factor of 4 more drag doesn't mean it's 4 times more efficient because it's only one factor in the entire equation. But experimentally we also saw that with this helicopter, the maximum thrust you can kind of sustain inverted is about 10% higher than the maximum thrust we could sustain straight up. All right, so then if you want to do something like flipping, the question becomes what's the reward for flipping, right? For hover, we saw what the reward was, but for flipping, it's going to be something different. We started working on this, we said, well, okay, it's really difficult to design controllers that work everywhere. So a common approach to these kind of problems is to say, rather than designing a controller that works for the entire space, pick a target trajectory. And then learn or design a control policy that is good at sticking to the target trajectory, even in the presence of wind gusts and other perturbations. Okay? So then somehow specifying the task is a matter of specifying a target trajectory. And then also a reward function that tells you how much to penalize for each possible deviation from that target trajectory. So we did that. We specified a flipping trajectory that seemed to make sense. The helicopter has to flip in place, but flipping in place is actually not possible. Because as you're rotating, you're not generating vertical thrust when you're this way, and so you would sink. So you need to kind of pump yourself up a little bit, and then as you rotate, you're falling, and then when you're inverted, you pump yourself up again. And so we designed a trajectory like that, and then checked if we could fly it. Here's an experiment we did. What happened here is we designed our target trajectory. We had a helicopter model. It was actually estimated, the parameters were estimated from data collected from the helicopter. And then we ran essentially optimal planning in a market decision process. So we found an optimal control policy to stay on that target trajectory. In simulation, worked beautifully. Okay, what happened there? Okay, at a high level, and the quick summary is that what happened is the helicopter crashed. But at a more detailed level, what happened is we had a target trajectory. That target trajectory actually was not flyable because helicopter dynamics is so complex. We specified something and we said stay on this trajectory. And in simulation it was flyable, but our simulation isn't perfect. And so it knows in simulation I'm trying to fly this is not possible. So as it's trying to get back on track, it's not succeeding. And it's exerting the controls more and more to try to get back on track onto something that they actually can't even fly. And as it's exerting the controls more and more, it starts oscillating around that trajectory that it's trying to fly. At some point, it's exerting the controls so much that the engine is not able to push the blades around anymore. The thrust it needs to generate is just too much. The engine just dies at that point. And that's when the sound goes quieter. Engine's not working anymore. The blades are going very, very slow, so generating almost no lift, and it's just like a brick dropping from the sky. It is true that in principle you can save a helicopter, right? So you should be aware of this. If a helicopter's engine dies, you can often still save it. The way you do is use something called auto-rotation. What the idea is there is that, well, think of something like a windmill, right? Wind goes through the windmill, it somehow absorbs energy, and it spins, right? You can imagine doing something similar with a helicopter. You say, well, if I drop down, that's like air going through my windmill, so to say. I absorb that energy in the blades, which are then spinning very fast. And because they're spinning fast, they have friction and so forth, and there will be some friction on the way down. And so I will be absorbing altitude energy into friction and drag. My blades will be going really, really fast when I get close to the ground. And then when you're close to the ground, what will happen is you'll say, oh, my blades are going fast. That's great. Let's change the angle of my collective from 0 degrees or very low degrees to a very high degree. All of a sudden, you generate a lot of thrust. Pushing air down, it slows down your helicopter from falling pretty fast to almost 0 speed. And then your blades will have stopped spinning because all that energy in the blades went to pushing air down. Hopefully you didn't pump your helicopter up too high. You just slowed down a little bit, enough to then drop on the ground and land. So that is possible. You can do that. Good pilots can do that. Usually the way it happens is you actually come in more like an airplane. So if your helicopter is going fast enough, it gets some lift the way an airplane gets lift. So you can kind of glide around. You keep your blades spinning through the airflow through it. And then when you're close to the ground, you kind of angle back, crank up the collective, and now your forward speed, you come in with a lot of forward speed, not vertical speed, but a lot of forward speed, a lot of forward speed, then gets slowed down by that thrust, and then you drop on the ground. So that's what you do in auto-rotation landing. There's other reason you would auto-rotate. You would auto-rotate if your tail rotor dies. You would auto-rotate, yes, if your tail rotor dies. If your tail rotor dies and you're in a helicopter, what will happen is your helicopter will start counter-torquing the body to the engine, and now you spin around to the blades and you'll start spinning around. It's impossible to control a helicopter where the tail is spinning around too fast. So what you do is you say, well, why am I having all this counter-torque? Because my engine is running. So what you do is you shut down your engine. Now you have no engine, no tail rotor, but that's all right. If you have a really good pilot, they can still auto-rotate it, bring it down, and land. Keep in mind, a successful auto-rotation landing tends to be one where people survive. It's not the kind of thing, like aiming for more is a lot to ask for. And for some helicopters that are very heavy, it's dangerous because you could come down, so you really don't do it for fun. You could come down and then everything that's above you, all those blades could kind of still have a lot of inertia and just kind of come through the cabin and hit you that way. So it's not something you do when you don't need to, but it's an emergency procedure that every helicopter pilot is supposed to know and be able to execute. All right, so what we said as well, this helicopter crashed, that wasn't great. We designed the wrong target trajectory. Maybe we should design a different target trajectory. And we tried and tried, but we actually didn't succeed in designing good target trajectories because helicopter dynamics is so complex. Then we went to watch this video, Sunday at the Lake. It's a great video. Alan Szabo, one of the world's best RC pilots. He's just flying this helicopter in all kinds of acrobatic maneuvers, and it works out just fine for him. So we're saying, well, it works out fine for him. Why doesn't it work out fine for the computer? It's the same kind of helicopter, right? We're doing something wrong. We need to do better. We hired ourselves one of the best helicopter pilots in the United States and said, well, how about we collect trajectories from this pilot? Because whatever this pilot is flying is a trajectory our helicopter can do. So we don't need to design the trajectory by hand anymore. We can just record it. And now we have a feasible trajectory that in principle we should be able to fly. Now, when a pilot demonstrates, often they don't do things exactly the way they might want to. So what we said is, well, we know probabilistic reasoning and so forth. Let's collect many demonstrations and then use probabilistic reasoning to back out a denoised version of this set of demonstrations to try to get something better than the set of any of the demonstrations that were demonstrated. So here's what we did. Our pilot would fly. We would have all our HMM running to track the helicopter. And then we're now replaying 6 of those demonstrations in a graphical front end. So it is a result of tracking the helicopter. It's a graphical replay, but our pilot flew an actual physical helicopter. They're going through loops now. You can see they're kind of going through the same sequence of maneuvers, but not always at the same time, not always in the same direction, not always in the same location. A naive thing would be to say, well, let's just average them all. And that will give us a denoised version. Often averaging denoises things. The tricky part with averaging, though, is that if you have a nonlinear dynamical system, if you average trajectories, you get something that doesn't satisfy the dynamics anymore. Averaging only works if you have linear systems. Helicopter dynamics are not linear, so averaging is not good enough. But intuitively, there's something going on there. There's a pattern, and we should be able to extract it. So here's how we extract the pattern. We say, well, let's build an HMM-like model. Now, the hidden state corresponds still to helicopter position orientation, velocity, angular rate, but it's now a sequence of states that corresponds to what we think is the pilot's intent, what the pilot is trying to achieve. And they're connected from time t to t plus 1 with the helicopter dynamics model. Then the actual demonstrations are observations of what the pilot was trying to do. And then we somehow want to hook those up, right? Somehow build this into an HMM. But the demonstrations come in at different paces and so forth. So we can't just hook them up in a linear way. We have to do something a little more advanced than that. So let's see what we can do. We have something that looks a lot like an HMM, but we want to hook up these observations. What we do is something called dynamic time warping, also known as Needleman-Wunsch. What this is, it's an algorithm that can align two sequences. So we would align the intended trajectory, the hidden trajectory here, with demo 1. We would align it also with demo 2, right? And once we do that, we have a nice aligned set of observations. Of course, I filled something in here that, you need to know what to fill in there. I just filled something in to kind of bootstrap the whole process. We pick one of our 6 demonstrations, fill it in, align everything to that one demonstration. Once we've done that, everything's lined up. And now we can get rid of it. We don't need it anymore because we have the lineup. Now we can run standard forward algorithm in this HMM to find out what the most likely intent was of the pilot. Because it's a continuous state space, it's an extended Kalman filter rather than just a standard forward algorithm, but it's really the same thing, just with integrals instead of summations. All right, then you might say, well, but this alignment, was this really the right alignment? Well, maybe not. So let's get rid of the alignment, realign to what we found now, and iterate till this whole process converges to something reasonable, okay? Assuming we did that, we now can watch what we get out of this. So we have still the colored helicopters being the demonstrations, but time aligned now, and the white helicopter is what we extracted as the intent of the pilot. To look at this closely, and if you're, I guess, have watched a lot of these helicopter trajectories, you'd say, well, yes, the white one looks a lot better than the other ones. Now, looking at it from a different point of view, what you see here is a double loop. You see 3 of the demonstrations, and you see the extracted intent of the pilot in the black dotted double loop, which is a much cleaner version than any of the demonstrations. This without putting in any knowledge. The algorithm didn't know it was trying to do loops. It just said, here were a couple of noisy demonstrations of what's trying to be done. Get me out what likely the intent was of the pilot. Okay, put this all together. With a side effect of doing all this aligning is that you can actually build a very nice dynamics model of your helicopter. Once you have all these aligned demonstrations, you can see the consistencies in how your simulation is going wrong across demonstrations in predicting the behavior of the helicopter, and you can improve your simulation model. So we now have an improved simulation model. We have an aligned, a target trajectory found from aligning demonstrations and denoising them. So now we have everything that we need to kind of solve for an optimal control policy and see how well it works. So here is fully autonomous. Yeah. 2 of the demonstrations. 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 2 to do with this approach was fly the entire flight envelope to the extent that we had pilot demonstrations available of flying there. It's possible that helicopters have some part of the flight envelope our pilot couldn't fly, then we would need to find another pilot, but our pilot was quite good, one of the best in the United States, and we could fly any maneuver our pilot could fly, learn from about 5 to 10 demonstrations. Usually be 10 demonstrations if we pick the 5 most consistent ones, and then run the algorithm over the 5 most consistent ones, and it would have learned to fly those maneuvers. Any questions about helicopter flight? Okay, now let's briefly look at legged locomotion. So what we're looking at here is a robot called Little Dog. Looks a lot like a cockroach. The challenge here, is to get this robot to walk across non-flat terrains. What people were able to do before we started working on this is to get these robots to move feet into a new location. But what was difficult was to decide what sequence of footsteps is the right sequence of footsteps to get across. The challenge we're looking at is, given that we already have controllers that can, let's say, balance a robot on 3 feet and move the 4th foot into a new position that's being asked for, what position should we be asking for that 4th leg to be placed? We worked on this for a while. This is essentially, again, a market decision process where you have reward associated with each possible placement of the robot on the terrain. Now, we tried to tweak the reward function by hand. We said, well, what reward function would be the best reward function to use here? You want it to relate to stability, right? You want the center of mass of that robot to be within the support triangle of the 3 feet that are placed on the ground. Not just within the support triangle, but with some margin. So you want your reward to be higher when there's more margin. That's not the only thing that counts, because then you'll just stay in place. You want to make progress. You want the height differential between your feet to be not too much, because that would make for an unstable pose. You want the slope underneath each of the feet to not be too much, because that would, again, not be a good thing. It'd be sliding and so forth. Overall, there were 25 of these features that we came up with. And now the reward function would be a weighted combination of those features. We tried to set those weights by hand. Was too difficult. Tweaking 25 numbers by hand is a lot of work, very difficult. So we said, how about we try to learn those weights? So we're now learning the weights of the reward function. The way we do it is by first demonstrating how to get across. We would click on a terrain and show a sequence of footsteps that get you from start to finish. Not just a line sequence, but a sequence of footsteps. Then we run apprenticeship learning, which we've seen before for Pac-Man learning from somebody play. There we learn a Q function. What we learn here is a reward function. What that means is what you learn is a set of weights such that if you now find the optimal policy in your MDP using that set of weights to define its reward function, that optimal policy will match up with the demonstration. So you're backing out the reward function from observing the optimal policy. So it's the reverse problem from what we looked at before. We go from optimal policy back to reward function. Well, then the way it's being used is you're presented with a new terrain. On the new terrain, we can now compute for every possible pose of the robot what the reward would be, and now we can run optimal planning, so solve the MDP, and find a path of footsteps across. Here's what happens if you have a bad reward function. The reward function that is equal to all possible poses of the robot across the terrain. Robot tried very hard, but it was putting its feet in the wrong place. And as a consequence, when it slides a little bit, which is invariably going to happen, it gets stuck and can't get out. Here's what happens if you learn the reward function. Now using the reward function to learn from demonstration. Look carefully at the feet. They're still slipping and sliding, so whenever that happens, they're slipping and sliding in a way that doesn't harm the robot the way it did before. And this at the time was the fastest way of getting across this type of terrain. And this is real learning, by the way, that we did here, in the sense that this was a project run by DARPA, which is a Defense Advanced Research Project Agency, which gives out money for research. And this terrain was at their site. We didn't know this terrain. We had our own terrains. On our own terrains, we would demonstrate. On our own terrains, we would then learn a reward function for our own terrains, but feature-based, so we can generalize And then when DARPA presented a terrain that the robot never seen before, we'd never seen before, it could compute the reward function for that new terrain and actually do quite well. All right, next time we'll look at final contest results. We'll look at robot butlers, and we'll look at where to go next at Berkeley to learn more AI. See you on Thursday.